So for being here, my name is Vladimir Vishnevskii. I would like to offer this talk that is called C++ in the World of Embedded Systems. Originally coming from the area of high-performance distributed systems, I then switched to embedded field and spent there several years. And since a while, I was thinking about making a talk with some overview of embedded systems, covering some problematics and architectures in embedded systems, with focus on C++ availability and applicability and potential of C++ language in embedded environments. The motivation for this talk is to encourage knowledge and experience exchange between the two different worlds of software engineering and embedded engineering. Software engineering world that is for me highly associated with C++ due to my background is the world where that is interested in rich language features, practices to improve software, and embedded engineering world is a fascinating world where huge knowledge and experience in hardware-software interaction and low-level optimization and development is accumulated, but where the software is quite often secondary thing. And I think that just increasing this overlap that's already there, but can be even further extended, is mutually beneficial. Let's dive into the topic. So what is embedded system? So embedded computer system is a specialized system that is designed as a part of another system. So we see multiple examples. The modern vehicle has a network of electronic control units, ECUs, that control different parts of the car. We also hear about the different devices that are labeled as smart devices. They have some embedded control elements, and this can be some smart kitchen appliance with some logic, or it can be a smartphone that has the functionality of the mobile computer. To describe different specifics of different embedded systems, I would suggest to define some groups of the systems that share characteristics. In the context of this talk, I would like to highlight the following groups. The group of the systems with limited resources. So there is no metric that can be used to distinguish if the system has limited resources, but at the same time, as the system is specialized, and also most likely there will be requirement to reduce production costs, to reduce energy consumption, also potentially reduce the device size, the one should expect that there will be no abundance of operational memory, of the storage for executable flash memory, and in general computational performance. The second group are the real-time systems. So similar to non-embedded, the real-time systems this is a large group with several subgroups, but in general, we'll be saying that it's the system where some of the functions should be performed with respect to some deadlines. To achieve this, it is important that these real-time functions have the upper bound for the execution time in worst case scenario. To make it feasible, the system should have the deterministic behavior property so that it should switch between some predefined set of states, and execution path from each state should be also well defined. The third group would be systems with some criticality. For example, safety critical, mission critical systems. What is important is that the design and implementation of those systems have to follow some specific guidelines, including coding guidelines. The fourth group is basically everything else. There are many embedded systems that are based on the embedded versions of general purpose operating system, offering some HMIs, for example, like ATMs or entertainment systems within the cars. Development for those systems is done in the framework of operating systems on which they are based, and might be not very different from the development for servers or desktops. We will not be covering this in detail in this talk. So now a bit about the embedded development process. So we are mostly talking about the cross-tooling. So because the target architecture most likely will be different from the architecture on which the developer works. This increases, as with other complex software systems, increases the deployment time, also increases the feedback time to get for example, from system validation. Also, diagnostics and debugging can be limited. It either can be limited due to platform limitations or for security reasons, or the system can be just hardly accessible. Also, what is possible is that the improvement of hardware will be happening in parallel with the development of software. So hardware can contain some bugs, some issues. And compilers and tooling can also have some defects, especially some proprietary solutions. They can have problems that can stay there for quite a while. So conclusion from this is that the code quality of embedded software should be maximized prior to deployment. And the best practices are relevant and crucial for embedded development as well. And so test-driven development review practices, this is important. Also, this would definitely improve the developers' productivity if that will be possible to perform the primary testing and develop the code for embedded system without on the developer's machine. Actually, for example, in some at least unit test environment. This requires portability. So now a short review of terminology, and for those who are interested in the topic but have attached this before, some short introduction in the hardware that can be used for embedded solutions. So here we see some microcontroller core. It has the pins, input-output lines. They are called general purpose input-output, GPIO. They can be grouped in the port. This is not the port as in the port-bound input-output in x86, for example. This is just the terminology that is used. Those lines, the state of those lines, they can be accessed or modified using the memory mapped input-output. This is, or MMIO. The state of the line is mapped to some bit or set of the bits in some specified memory allocations. So modified value by this address will modify the state of the line or access the state of the line if we read the state. So several, so those memory allocations responsible for some line supports can be grouped into, can be named as special function register, SFR. This is not the CPU register. It's also terminology that is used. So the core can have also some components that already perform some functionality. For example, it can contain some timers or some communication components, like here, integrated universal asynchronous receiver transmitter. It will be also controlled via MMIO. So some bits will control the state if it's activated or not, or some bytes can be used to transfer data over it. And it also has its own lines, but they are not general purpose. They are used for transmission using the UART. On this trivial hardware, the trivial software can be deployed. So, and it can be organized in a way that the signals from connected devices will be transferred to application logic via mechanism of interrupt service routines or just by polling of MMIO registers. The interrupt service routines are the routines that can be registered to be triggered when some event in the system occurs. For example, line state change happens. And the application logic that is based on the loop will be just controlling the state of the peripheral devices or internal devices by polling the MMIO registers or accessing the global objects that are modified by interrupt service routines. What is interesting that due to its simplicity, this software architecture can really work in the real-time applications because it can be done that it will have deterministic behavior. So if there will be need to extend the functionality of the software, then or to add some communication components and some diagnostics or maybe some application-specific logic, then the simple architecture will scale to something like this. There will be need to introduce some preemptive priority-based scheduler that will control the set of predefined tasks. Those tasks, they will be already known on the design time, and they will have static priority. And what is important, they will work with some exclusive set of resources, including memory and peripheral devices. The communication with the tasks and between the tasks will be happening via the queue mechanism. So the task will be servicing the queues. They will be always ready to process the events. So there will be no busy waiting. In case of delay, they will schedule some delayed work. And one operating system task can have multiple logical tasks. So on the base of these queues, the non-preemptive event-based multitasking will be implemented. So what we can see here, we see that there is a task-based parallelism with some dedicated narrow specialized tasks. Also, there will be the system is reactive. There is an asynchronous interaction via the queues, and the resource contention is minimized, and also including the access to the memory. So this is similar to actually problematics of the high performance applications, and this is we can see that high performance and embedded applications, they share some characteristics. Let's now discuss what are the requirements to the language that can be used to develop embedded applications. So we can list here the minimum overhead due to the resource limitations. Also, portability and test friendliness would definitely aid the development process. Availability of reusable frameworks is quite important because it would be great to focus on development of the product instead of re-implementing the basic utilities. And I think we can agree that C++ satisfies those requirements. Zero cost abstractions plus tooling that is available for various platforms. Also, possibility to inject dependencies and make the code test friendly. And third-party frameworks are also available for the language. At the same time, there are some limitations for C++ applicability for various embedded platforms. We should consider that compiler support for particular platform can be limited. Also, for some platforms, the standard library can be available only with some limitations. Also, some programming elements and constructs that are not completely relevant for the language, but at the same time can be considered risky for some platforms, can limit the applicability of the language. We will come back to this a bit later. And also some industrial standards limitations. If we look at the compiler support, so here in the recent years, significant progress has been done. And even proprietary solutions, they already support at least C++ 14. Of course, this is not the most up-to-date standard, but at the same time, it enables development of more or less modern C++ code. Of course, the open source solutions like GCC, they offer the best support and already C++ 20 or even 23. At the same time, all of them still have some gaps even in the syntax support. Regarding the standard library, so according to C++ standards, standard library can be available in two variants, hosted and freestanding. Hosted variant contains components that are dependent on OS. Actually, hosted is the full standard library. The components that are dependent on OS, like file system or thread, the dependencies for them should be satisfied by the actually underlying libc that is used to build the standard library. So it's not necessary that the real OS is present. At the same time, as for many embedded platforms, the file system or thread thread components will not be available. These libc for those platforms, or in some cases even compilers during building the standard library, can provide some placeholders for missing headers and declarations, and those components will be present to fulfill the standard requirements, but they will be unfunctional. For most popular platforms, for the open source solutions, it's possible to get or just build the hosted variant of the standard library. The freestanding version is the second option. It is the version that is supposed to be not dependent on OS specific components. Apart from the OS dependent components, it also excludes the actually whole STL and utility lib. So even utility header with std move and std forward is not there, so it cannot be. So it doesn't even support the core language features. It's actually hardly usable, unfortunately. And according to standard, there is no granularity. So only to those two variants, but some proprietary SDKs, they offer some subset of standard libraries. So they cherry pick those components that are just working. It is also possible that the standard library will be completely absent for some parts of the for some particular platforms. This can happen. Now, getting back to this, to some constructs that limit the applicability of the language. So for some platforms see some programming constructs to be risky. For example, heap allocation for limited resources can introduce unacceptable maintenance overhead and make some parts of the memory unavailable due to fragmentation. For real-time system, heap allocation, as heap is shared resource in case of multitasking, introduces risks that due to fragmentation and unpredictable fragmentation and necessity to synchronize access, there can be loss of determinism. Exceptions can also be seen critical for limited resources as they increase the executable size, and for real-time systems, they can increase. So it might become harder to analyze the complexity due to introduction of some implicit control paths. Also, that can also lead to some potential loss of determinism, and depending on the implementation, exceptions can also introduce some performance overhead. So those constructs, they are seen differently by industrial standards. For example, heap allocation is seen quite critically. So, for example, Joint Strike Fighter Air Vehicle Standard, GSF, the one from 2005 that was developed in collaboration with Bjarne Stroustrup, so quite famous standard, it allows heap allocation only on the initialization phase of the system. Then the heap allocation shouldn't be used. Automotive standard MISRA C++ does not allow heap allocation at all. This is the standard from 2008. And the standard, another automotive standard, AutoZAR C++ 14, that was developed in 2017, that covers C++ 14 standard. It requires that the allocation functions have deterministic behavior. So this makes it impossible to use the global shared heap. In case of exceptions, it is not seen that critical. So in 2005, when GSF was developed, it was concluded that the available tooling does not provide the adequate level of support for exceptions. and it was decided not to use them, but to other automotive standards, they allow to use exceptions, but require that they are used for handling of the exceptional situations. So what they are designed for and how they are recommended to be used in the core guidelines. Okay, so now we covered the C++ availability and limitations. Let's now go to examples. And as examples, I would like to cover, first of all, would like to revisit the device drivers and especially MMIO abstractions done via metaprogramming. This is not a new topic, but I think it can be interesting. And also, as a second example, I would like to go through some elaboration of the development or design of this event queue to cover how the containers and utilities can be used under the constraints of heap allocation and exception usage. So let's start with the device drivers. So here we can see a listing. This is a part of the SDK for some popular but really minimalist platform. And this SDK is developed in C. It's based on macroses, and it facilitates the access to MMIO registers and control of the GPIO devices and GPIO lines. So it contains the facilities to calculate the addresses, providing some constants that are specifying where those registers are located. Also provides the facilities to calculate and just to build the mask, and then the modification of the state of the register is happening just by applying the bit operation with some dereference address. This C-based implementation has some issues. First of all, the API code and the code dependent on this API can be executed only on target platform because the constants, they are just hard-coded in the code. Also, we saw that the layout of the system in form of the addresses and also the sizes, it is available on the compile time, but no checks are performed, for example, for offsets if they do not violate the sizes of these offsets in the mask, if they don't violate the sizes of the register for which they are applied. Let's elaborate how this can be improved using C++. First of all, we would be beneficial to define some strategy to evaluate the addresses. This can be done as a template that will accept the parameters of the address as non-template parameters, and also an integral type that will correspond to the addressable memory block where the register is located. Then, of course, the address calculation would just look like this, and the address will be reinterpreted to provide to be an address to the addressable block. So this strategy, this abstraction, can be then set up to be used in specific architecture by providing some of the parameters, like in this case, a SFR offset is a constant that is taken from the SDK for the platform. And also we can specify an alias for some complete architecture using the terminology that is used there. Then partitioning the namespace, we can follow the layout of the system, and we can also introduce another type that would be responsible for the write operations to the register. And that will be dependent on the strategy that will be providing the address. Here it will need these abstraction, this strategy, and also we will specify the offset and size of the register within the memory cell. Then it can be implemented in the way that this object, that this class will have a nested class that will allow to list the bits that we would like to modify, so to form a mask. And this would already have the method to set. All these memory-related operations will be just encapsulated in all these objects. This is just one approach to the implementation, but this is a demonstration that all the parameters that are involved in those operations, like platform specific and what the client code provides, they are available on compile time. This enables compile time checks. For example, here the offsets of the bits that are supposed to be modified can be checked not to violate the bounds of the register. We can use enable if, or the static assert can be used depending on what should be achieved. Also, there is potential for optimization. If the register is supposed to be completely overwritten, then there is no need to preserve some bits and to read, modify, and write back the contents of the register. It can be just assigned by some value that will produce less code. If const expression is used here, if this C++17 feature is not available, then text dispatching can be used instead. So the advantage of the abstraction for memory access is that for testing purpose, it can be substituted by some mock strategy that will provide the address of the object with static storage duration instead of the register address. And it can be used in testing in a way that it will be injected as a template parameter, and it will depend on some static object address that can be also provided as a non-time template parameter for our mock strategy in the following when the address is taken in the following way. And then we can check that the expected modification really happens using some here for instance, we are using GTest framework. So the layout of the system that is based on these abstractions can then be generated from the SDK C code or some documentation or specification files. And the classes representing the MMIO then can be used to implement more complex pieces of software, like drivers, for example. As we mentioned, it would be great if would be possible to implement those drivers using test-driven development approach to maximize the amount of code that can be produced on the developer's machine without actually just prior to deployment, and also can be verified. So the question would be how to inject those dependencies on these components into the more complex software parts. We have several options. So, for example, callbacks in the form of the legacy C-style function pointers or C++ functional objects. We can use runtime polymorphism and be dependent on the interface, or we can use compile time polymorphism. So callbacks and runtime polymorphism, they introduce some extra indirection that will inflict some overhead. It will depend on, depending on the compiler ability, some of these options can be optimized. For example, your virtualization or link time optimization, but this depends on the compiler functionality. Compile time polymorphism will not introduce indirection and will not introduce a virtual call, keeping the code available for further inlining and further optimization. In application to Also, yeah, there will be no need to build some hierarchies as with runtime polymorphism if those hierarchies are really not needed. In application to our device driver development, this can be used in the following way. So the component that will be under development, the UART control, can then be made to be generic and dependent on the type of the object that should be injected. So then instead of the real implementation, just some mock can be injected, and the as long as it is fulfills and has the same interface, it can be used instead of some real object. Then the expectation can be called on the mock, and the mock object will can be used to initialize the driver. And here I even omit the template parameters because they will be deducted from the parameters of the constructor. So this enables unit testing of the device driver. Yeah. So small intermediate summary. So we saw that it is possible to develop testable and portable software based on metaprogramming and compound and polymorphism, low-level software. It is also I'd also would like to mention that these and on my abstraction topic, it is definitely not novel. So there were several frameworks developed. Some of them are maintained, some of them are not. None of them became some form of the standard, de facto standard for these particular applications. As the language goes further and also the language support and the tooling goes further, this topic maybe can be revisited and can be interesting for some metaprogramming gurus. Yeah. So yeah. Let's switch to the next example. Let's go through the development of this event queue loop and see how we can use containers and what problems do we have with memory management and exception, what other ways and workarounds for the platforms where they are not available. So let's now see what we would like to achieve. One small remark. So we will be developing some reusable queue. It will not be fully optimized for performance, but it will allow to use it in multiple applications. If this queue is supposed to be used in some more performance critical parts of the software, it might happen that there will be need to build it in a different way. So how the reusable queue or loop could look like? Yeah, so we could introduce some generic event loop that can be configured by providing some template parameters, and then the run function can be invoked in the main function of the task that would be servicing this loop. And the client code can then just use can just schedule the work in the form of the closure. This doesn't look like that it is really hard to implement something like this, especially keeping in mind the power of the components of the standard library and some third-party libraries. But considering the limitations that we discussed before, like heap allocation or limitation heap allocation or an exception usage, this can become more complex task. If we cannot use heap allocation, we need to opt for some alternative solutions. What is available for us here? So we can use following approaches. We can use only objects with automatic or static storage duration. We can also use objects or potentially containers with embedded static storage. We can also implement custom allocation. So providing custom allocator or overloading the new delete operators, or use pool allocation, that also some form of the custom allocation, or just use intrusive containers for containers. Those are the containers, they do not own the objects. The question would be if any of these techniques is supported by the standard library or third-party libraries. For standard library, for STL containers, the heap, the usage of the heap can be avoided if the custom allocators can be provided. This is available. So, but some of the components of utility lib, like for example, std function, they do not support this. For example, std function version that accepts the custom allocator was deprecated in the standard and cannot be used. Also, some components of standard library are guaranteed not to allocate, like for example, std optional or std variant. Exception handling. So exception handling is not configurable in standard library. So there is no standard customization that is supported by standard library. And typically the std abort is invoked if the program is built without exception support, but the exception is thrown. Let's look at the boost. So probably the first third-party library that pops up when we are talking about C++. There are several components there that can be used without heap. Like, for example, some components of container library or intrusive library. Some components can be used to facilitate implementation of the custom allocation, like components of the pool library. Depending on the component, some components offer some customization for the handling of exceptional situations. Like some components of container library, some libraries are not dependent or on the exceptions, and so not explicitly dependent on exceptions, and can be used without them, like intrusive and pool. At the same time, there are explicit dependencies on some headers that belong to either freestanding or hosted version, like cstd-dev for freestanding or functional for hosted versions of standard library. So boost cannot be considered as a substitution of the standard library, as it is dependent. It's more like a complement for it complements it. So another library, another framework that I would like to mention here is ESTL. This is Electronic Arts Standard Template Library, originally developed for game development, but as we saw as the problematics overlap, it can be also adapted to be used in the embedded environment. It has some components with the prefix fixed underscore in their names that can be used without heap. Another third-party library is called ETL. This is Embedded Template Library, is designed to be used without heap allocation. Those two frameworks, they are based on some different design decisions, and they both have some distinct features, but the core functionality that they offer, it overlaps. They both also contain alternative implementations of standard utilities and algorithms. So they also both provide the same options for handling of exceptional situations, either exception throwing or custom assertion handlers, or completely disabled checks, internal checks in the containers, and full reliance on external checks. they do not contain explicit dependencies on standard headers. They use alternative implementation of standard utilities, and they both can be adopted for different platforms by injecting the required definitions. So let's see how we then can implement something like our event queue or loop using the facilities from these libraries. So first of all, we need to describe the event. To describe the event, the best way, the most reusable way would be just to store some closure that will describe the work that will be done as soon as the event will be serviced. So we cannot use std function. As we discussed, it requires the space to store the capture list, but the version with this custom allocator is not available. We need to use alternative. ESTL offers alternative that is called fixed function. It has the static storage for the capture list, but it requires the trade-off. So we need to specify the maximum size of this capture buffer. Also, fixed string is alternative for the string, as string in general case allocates the memory. There are some optimizations, but it needs memory allocation. Also can be used instead of the string. Here in this example, if some extra debug information associated with the event is needed, then it can be stored in the form of this fixed string. Then we need to store our event somewhere. So we can try to use standard vector for this. But we need to provide custom allocator that will provide and return the allocated space, statically allocated space once. And the vector, our client code actually will need to request the space once. This is needed because std vector, it does not support the semantics of extension of the storage. That means that all the storage that is supposed to be available in the future needs to be acquired before the vector will be populated. Then overflows are either handled in the allocator using exceptions if it is possible, or some redundant checks, some redundant external checks should be done to avoid getting into overflow condition. The checks will be redundant because internally in the vector will be also some checks for the necessity to reallocate. Alternatively, the out-of-the-box solution can be used. That is called Boost Static Vector. That is part of the container library. It has the so it is based on the Boost vector with the allocator that supports the static allocation. It has fixed capacity. It is compatible with STL, and we need to specify size at the compile tab. Alternatives are available in other third-party libraries like STL and ETL. The handling of overflow can be also configured and independently for the vector, and it's can be either exception throwing or there will be an assertion that will be triggered. This static vector then can be used as a backend for standard priority queue adapter. If the standard should not be used or is not available, then the alternatives are available either in the Boost as well or in the other third-party frameworks. So then also redundant checks, because in case of the static vector, the checks also will be present internally and they cannot be disabled. So to not to get into the overflow condition. So the priority queue, it is based on the heap data structure. So it swaps the items on insertion and extraction. This can become expensive because the object that we store in our vector that is used in the backend, it increases in the size because it has all the objects that it owns also have the static storage. So the static footprint of the object increases. And this can introduce unacceptable overhead. So that might be that there will be necessary to consider some node-based container to maintain the sorted order in the queue. So we can use the set for this purpose. Set is the tree-based container and that needs to allocate the items, and the option from ESTL that is called fixed set supports the static allocation. It is also required to specify the maximum capacity of this container, and the capacity of this container is the maximum size. And if the heap should not be used, can also specify that the heap allocation fallback in case of overflow should be disabled. We then can use, we can use external checks. And in this case, in case of ESTL and ETL, the internal checks can be then completely disabled. So the client code should be responsible that there is enough space. Another alternative regarding containers and heap allocation, containers without heap allocation is usage of the intrusive containers. Those are the containers that are built on the principle that the data that is needed to plug in the element into the container is already embedded in the stored type. So here, event object is inherited from the set base hook, and then the set is specified to store the event. Also with the predicate to compare the items. What is interesting is that intrusive container does not own the object, so it does not control its lifetime, it doesn't allocate memory for it. And also, because of this, there's no need to specify the maximum size. So this is the only option that is fully dynamic, so that as it doesn't own the objects are owned by some other components, but they can be added into this data structure. Here, as the second part of the example, we take care of the allocation for the items and creation of the items. Here it is shown how using the components from the boost pool, the simple pool allocation can be implemented. So the aligned storage for some n items can be turned into free list pool using the component that is called boost simple segregated storage. This is a simple implementation of free list that will allow to perform allocation and deallocation of the objects of the fixed size in the constant time. Then allocation can be done, and the item can be then plugged into the container, and no further copying or for the allocation and copying will happen. Of course, it is also possible to implement custom allocation for event type, but there is an issue with this because the events are serviced in different tasks. But the new and delete operators, they are implicitly static. So that means that they will be accessing the same allocation facilities from different tasks, basically inflicting resource contention. This can be avoided if the event will be made generic with non-time template parameter that will specify for what task the event, in what task the event is supposed to be serviced. And then the different instantiations of the events for different tasks will access the different instantiations of the allocation facilities. Like in case of this event allocator here. So there are also some patterns that are based on the types that are guaranteed not to allocate, that are extremely useful in the embedded environment, probably not only in embedded. For example, the polymorphism that is based on variant. For example, here we can see that there is a factory method that returns one of the transport types that implement the transmission using one of the low-level protocols, either SPI or UART. It can return the variant that stores either SPI or UART objects. And based on the runtime information, it just returns the variant that store the exact type that is needed. Then switching to then applying the visit function with generic lambda, we can switch into some form of the duck typing mode, and the call will be of the type that is of the type that was of the real type that was returned by the factory method, by the factory function. It implements a form of the runtime polymorphism without necessity to have some inheritance and virtual calls. Also, there is no need to allocate memory in the factory function for the object that it returns. Also, if especially we want to avoid the exception, error handling requires some appropriate patterns. For simple cases, STD optional or optional alternatives from ESTL or ETL from Boost can be used. This pattern allows to avoid some returning of the Boolean type with some output parameter that quite often can be seen as a simple solution for error handling, and that seemed quite problematic not only for embedded as well. And so optional can be returned from the function that it can be checked if the result is available, and then the return type can be further processed. The further development of this would be some form of the variant that can store the return type, or some error code. That can be either the standard error code or some other error code. This will be some form of the imitation of the expected type that is not yet available in the standard. Boost outcome is an alternative solution that is more advanced. Some intermediate summary for containers, algorithms, and utilities. There are some limitations, but to some extent, standard library can be used in embedded environments. It might be the third-party libraries actually offer better solution in this case, but anyway, it is possible to use it. So also the third-party frameworks, they really offer a rich choice of standard-like and non-standard containers and utilities that have options without heap allocation and that can be used without exceptions as well. And if the standard library is not available or some components are not available, those third-party libraries can be used to complement it or just completely substitute it. Okay, and now overall conclusion. Yeah, so the best practices that are well known to the C++ community are really essential in embedded development. C++ language has mechanisms that enable testability and portability of the embedded code. Yeah, we can build code, we can combine different components by encapsulation, we can by polymorphism and encapsulation. This is beneficial. Also available. Also, there are multiple third-party frameworks, as we saw, that can be used in embedded environment and can solve standard problems. And there is definitely an overlap between embedded and non-embedded domains, like, for example, HPT or game development. And this knowledge exchange is beneficial.